Good day, everyone. Thank you for joining us. Our first Cogent Live presenter of the day will be Chief Technical Officer, Dr. Brad Coomer. Dr. Coomer joined Cogent as employee number 6 in February of 2000 and has been involved in the design, planning, and implementation of the Cogent network since its inception. Prior to that, he spent 25 years at Bell Labs in the optical fiber research and development area, specializing in the development of new fiber types optimized for next generation optical transmission systems. On your screen, you'll have the ability to engage Dr. Coomer by contributing a question at any time. Submitted questions will be answered at the conclusion of his presentation. This session is being recorded and will be available via Cogent's website, www.cogentco.com, next week. Dr. Coomer, thank you for being here with us today. Let's begin.
Well, thanks, Rusty, and thank you all for joining us today. I hope that over this 2.5-day series of sessions, we're able to provide some information about Cogent and answer your questions. I'm going to start with a very simple question, and that's what makes Cogent unique? What makes Cogent different from other service providers? And the answer is actually very simple. Actually, that is the answer. It's very simple. Cogent has a very simple network architecture, a very simple business plan, a very simple and focused product set, and that leads to very simple operations, provisioning, billing. The whole structure of Cogent is built around simplicity. Let me first start with the network architecture. Simple network architecture. When we started the Cogent network, we started with a blank sheet of paper. We had no legacy network that we had to share or worry about how to reuse or revise. We designed an all optical network, designed and optimized from the very beginning to do one thing, and that is provide high capacity internet transport, internet protocol traffic. We have core routers in each market that are interconnected by a dense wavelength division multiplexing, DWDM 10 gig E and mostly 100 gig E intercity backbone. We have edge routers in each building that are connected to the core routers by DWDM or CWDM gig E, 10 gig E, or in some cases 100 gig E metro rings. The protection is done at the IP layer, no SONET, SDH involved. In fact, we started using the terminology IP over DWDM to describe this architecture back in 2000. That was maybe 10 years before Cisco and other vendors started adopting the same terminology. But that's been the fundamental premise of our design from day one. And if you look at it, it's really just a LAN architecture, very, very simple LAN architecture, but implemented on a global scale. We have simple cookie cutter configurations of our equipment, and that leads to simple network management and quick and easy provisioning. We also have a very simple business model. We have a simple and very limited product set. We sell dedicated internet access, that is layer 3, IP services, internet access. We also offer Ethernet transport, basically layer 2 services, and we've purchased some data centers, so we offer co-location. All of our products are delivered over Ethernet ports, FE, GigE, 10 GigE, 100 GigE, and we only target locations with a very high customer count where it makes economic sense to build this sort of high capacity network. So large multi-tenant office buildings, MTOBs, particularly in the US, carrier neutral data centers throughout the world. And we supplement these with our off-net products so that customers who maybe have a number of offices that are in our on-net buildings, but a few that aren't, can also take advantage of the Cogent network. We're a facilities-based network. That means we own all the equipment. But rather than spending hundreds of millions and sometimes even billions of dollars building a fiber, burying fiber in the ground and building a fiber infrastructure, we chose to buy 20 to 30-year IRUs. That's basically a long-term unbreakable lease on dark fiber that was already in the ground. So we bought a single pair of fibers to form our backbone network and multiple pairs of fibers in rings to form our metro network. So we're continuing to expand both of those networks every year. In the 1990s, there was a huge amount of construction or building of fiber optic cables. Basically, everybody that had some kind of right-of-way, railways, underground power cables, underground pipelines, even highways. If you had right-of-way, it was very clear that you could make a lot of money by putting some optical fiber cable in the ground and using it to provide services for yourself or possibly to sell. When I was at Bell Labs and working with my colleagues at Lucent and other fiber providers around the world, we were very successful, frankly, at convincing these folks that were putting in the cables that if you're going to all the cost to buy the right-of-way, to do the trenching, to install the network, frankly, if you only need a few fibers, it doesn't cost much more to install a few hundred fibers. It's almost the same cost. So because of that, there's a tremendous amount of dark fiber in the ground today. And we were able to take advantage of that. And we were creating Cogent by buying these fiber IRUs. This allowed us to achieve the lowest cost per routed bit mile in the industry. And that's been a driving principle behind Cogent from the very beginning, the lowest cost per routed bit mile. And this allows us, we have been, frankly, one of the main drivers who have driven down the cost of internet access worldwide over the past 20 years. Now, this business model really hasn't changed very much. The technology has changed. The scope of our network has changed. We've gotten much broader, much bigger. The products have expanded to 10 gig E, 100 gig E. The network has gotten bigger and faster. A lot of things have changed in the technology, but the important things about our network and about our business model haven't changed. Since the very beginning, the same business model, the same basic network architecture that was in place when Cogent was founded in 1999. In fact, it's basically the same architecture that Dave Schaefer sketched out for me on the back of a napkin when I met him at an optical fiber communications conference in 1999, and he described the idea that he had of creating this network. It seemed like such an intriguing idea that I decided to retire from Bell Labs after 25 years and come to work for Dave and help to build this next generation network, which in my previous job, I had been sort of studying where the networks were going. Now I had an opportunity to actually build one. So I look back at my PowerPoint archives and I ran across a presentation that I gave almost exactly 20 years ago. It was April of 2001 at an optical internetworking summit in London. And by the way, I really like the logo that we used back in, the big pipes, and that really sums up Cogent's business model very, very nicely. Well, here was a traditional network versus Cogent network slide from 20 years ago. It really hasn't changed. Our backbone network, terabit large core routers interconnected by a DWDM backbone transport system, buildings connected back to the core routers by a DWDM edge metro network or a metro network. Not a lot has changed since then. Let me talk about some of the changes in 4 technology areas: the core routers, edge routers, backbone transport, long haul transport, and metro transport, starting with the core routers. In 2000, we deployed what at the time were the largest, the biggest routers that Cisco had in their portfolio, the GSR, the gigabit switch router. And this had 10 gigs per slot. and you could buy cards that supported GigE and OC192 POS, packet over sonnet. The reason for that was these were the high-speed, quote, high-speed ports that were used to interconnect routers in different cities. And there were no 10 gig internet, 10 gig optical transport systems at the time. The transport systems that were in place, the equipment that you could buy, supported DWDM, Sonnet, and SDH at OC192. So the router industry developed this protocol called POS, packet over sonnet, to be able to package a bunch of sonnets and stuff them into a pipe that could then be transported over a sonnet transmission system. We were not using sonnet per se. We were not doing protection at the sonnet level, but that's the only interface that we had available for the high-speed part of the network. And in fact, in early 2000, when we first rolled out the cards, these OC192 cards had an OC192 POS interface, but frankly, the trunk side, the throughput of the trunk side was only OC48, 2.5 gigs. Later in 2000, Cisco introduced the updated versions that really worked at OC192 rates. And 10 gig ports were not available on that platform until about 2006. About that same time, we started migrating from the GSRs, which was a big, full rack piece of equipment, to a smaller Cisco, initially 6500 and then 7600 series routers that had a smaller footprint, lower power utilization, 80 gigs per slot instead of 10 gigs per slot. And in 2010, we migrated to the Cisco ASR 9000 or ASR 9K platform. And this has proven to be an extremely flexible and upgradable platform. There are 4 different sizes of these multi-slot chassis with either 4, 8, 10, or 20 line card slots per chassis. The larger chassis have the option of running different numbers of switch fabric cards, which give the router the ability to handle different amounts of traffic. And since 2010, over the past 21 years now, Cisco has gone through 4 generations of the route processors and switch fabric cards and line cards for this ASR platform that have each time increased the throughput of the routers. In 2010, the routers were deployed, the routers we were deploying then, the switch fabric cards and route processors could support 80 gigs per slot. That's 8 10 gig E's per slot. In 2012, new route processors were available, new line cards that could support up to 400 gig per slot. We were deploying 36 port 10 gig cards, 24 and 36 port 10 gig cards. And in 2013 or so, 2 by 100 gig E cards. Although that was our first introduction of 100 gig E ports in the network, although at that time, they were fairly expensive and not very cost effective. In 2015, Cisco introduced yet another generation of route processors, switch fabric cards that allowed to go to 800 gigs per slot. And we began deploying 8 by 100 gig E cards at that time that were much more cost effective and much more power efficient. And then toward the end of 2019 and all throughout last year and this year, we're currently deploying the 4th generation of cards, which Cisco calls Lightspeed, or actually they have called it the 5th generation. They initially had a Lightspeed and then a Lightspeed Plus, but these cards can support, depending on which chassis you're in, either 2 terabits per slot or 3.6 terabits per slot. And I think with actually the same route processors and switch fabrics can actually support a little bit higher, maybe up to 4 terabits per slot with some new cards that may be coming out in the future. But so we're deploying today cards with either 20 100 gig ports or 3600 gig ports per slot. In the edge router platform, let's go back to 2000 again. Initially, we were deploying what's called, or sometimes called, a layer 3 switch, or some people refer to it as a swouter, sort of a combination of a switch and a router. It's basically a switch, but has some limited layer 3 functionality. But the heavy lifting is really done at the core. So the ports at the switch were then mapped back to ports on the core router. In 2009, we added some different models of these swouters that could also support 10 gig ports. But in 2013, we made what was really a major change in the architecture of the edge routing platform. We just started deploying the Cisco ASR 9001 router. Now, this is a standalone 2RU router, so that means it's about 3.5 inches tall. It's part of the ASR platform, runs the same software as the larger ASRs. It supports full routing tables, supports MPLS, native IPv6. So now all of the heavy lifting is actually done at the edge of the network, which gives us some architectural advantages, particularly for our layer 2 product. And by 2015, we had converted the entire edge network to this ASR 9001 routers. In 2020, we began deploying a newer version of that router called the 9901. It's the same size, but in addition to GigE and 10 gig ports, it has a higher density of 10 gig ports and also supports a couple of 100 gig ports. And this is now the default router that we're deploying in MTOBs, in multi-tenant office buildings. We're deploying it today in some small data centers as well, but we're planning on migrating to a next generation of these standalone routers, sometimes called pizza box routers, the 9902 and the 9903, which will be available really in the next few months, I think starting later this summer. And these have higher density of 10 gig E and 100 gig E ports, much lower power consumption than some of the larger chassis. And we're looking forward to migrating to those for our small to medium size data centers over the next couple of years. Now, the routers I'm describing here as the edge routers are what we put in, let's say, a typical small to medium sized data center. Larger metro data centers, we use the same routers, the same large ASRs that we use in our core. Probably 15% or so of the large data centers have the core class routers, the multi-slot ASR routers. Now, before I get into the discussion of the transport layer, let me just spend a couple of minutes on reviewing terminology. And I apologize if this is well known to many of you, but I think we have a variety of people in the audience, and I want to be sure that you're familiar with the terms that I'll be using. First of all, what is optical transport? It's just the stuff that you use to interconnect routers, particularly the way you interconnect routers that are not in the same building. Metro routers that are in the same city, or maybe core routers that are in different cities. These all use some form of DWDM, dense wavelength division multiplexing. That just means that we're able to combine multiple circuits using different optical wavelengths or different colors of light on a single pair of fibers. We'll use the word OADM or ROADM. OADM is an optical add-drop multiplexer. That's just something that allows you to have multiple wavelengths on a single pair of fibers and drop off one pair or several pairs of wavelengths at a particular building. These can be either passive devices that just have built-in filters and are fixed and drop certain specific wavelengths, or they can be reconfigurable. That's a ROADM, reconfigurable optical add-drop multiplexer, and those are typically used in larger systems. Again, these OADM systems can be either passive, that is, there are no optical amplifiers, fixed wavelengths. Those are typically used in metro applications, maybe up to 40 or 80 kilometers, or they can be amplified systems, systems that require optical amplifiers and more sophisticated ROADMs for intercity. And basically all of the intercity networks, the long haul backbone is built using amplified systems, erbium doped fiber amplifiers and Raman amplifiers, and various types of ROADMs. Also, I'll use the term transponder. A transponder is something that is an O to E to O, optical to optical device that converts the so-called gray light or the light at some arbitrary wavelength coming out of a router into a specific DWDM optical wavelength. Now, in many cases, and I'll review that when we get into the details, we really prefer not to have a transponder. It's an extra piece of equipment. It's taking up space and power. It costs money, but it's providing the function that's needed to get these router ports, many router ports, multiplexed onto the same optical fiber. But the ideal is the true IP over DWDM model is to use a pluggable transceiver, basically a pluggable optic port that plugs directly into the router port and has a suitable DWDM signal coming out of it. And that provides the lowest cost and lowest space and power per bit. So our sort of holy grail is always moving toward IP over DWDM, getting rid of any transponders in the network. Also, I want to talk about optical transport systems. I want to differentiate between the two different components of the system. There is the optical line system. That's what transports the light. I talked about that's the optical amplifiers, the multiplexers, demultiplexers that combine the different wavelengths together, these ROADMs. That's the transport system itself, or the line system. And there are major technology advances here, maybe every 5 to 8 years. This doesn't change very often. But on the other hand, there are the DWDM optical light sources. This is what creates the light that you transport over the line system. And the technology changes there happen much more rapidly, typically every 2 to 3 years. And again, these optical light sources can be either transponders, which we prefer not to have, or pluggable optics, IP over DWDM. So let's look then at the evolution in the backbone line systems. Again, starting back in 2000, we deployed the Cisco 15800 system, which is a optical transport system that Cisco had acquired from Pirelli. This allowed us to transport 24 wavelengths in the version that we were deploying, but it was upgradable to either 32 or 64 wavelengths. And again, at the time, these were designed around 10 gig OC192 transponders. In 2007, we started switching over to a type of equipment that we had been deploying in the metro area for some time, but the Cisco MSTP, multi-services transport platform, or was later rebranded as NCS 2000, NCS 2K. These systems that we initially deployed starting in 2007 were optimized for 40 to 80 10 gig DWDM wavelengths over long distances. And we could go hundreds, even thousands of kilometers without regeneration on these systems. The 10 gig technology utilizes, to go long distances more than about 80 kilometers, you have to use something like dispersion, called the dispersion compensation modules. That compensates for the spreading that occurs on an optical system as it travels across the fiber. And in 2015, we began optimizing some of those systems for 100 gig. We backed off to 40 wavelengths, and in some cases we removed these dispersion compensation units, because while they're necessary for 10 gig signals, they are actually detrimental to the 100 gig signals. So we began modifying and optimizing some of the routes to support 100 gig transport. And then in last year, 2020, we began replacing some of those systems, and basically we've adopted as our standard for new systems that we're deploying what's called the NCS2K Flex platform. This is really optimized for even higher than 100 gigabit signals. And today we're deploying signals that are up to 600 gigabits per second per wavelength. So this will take 400 gigabit ports from a router, multiplex it into a signal up to 600 gigabit line rate, put that over a particular optical wavelength over the DWDM signal. And as these higher speed signals, 100 gig and above, use a technology called coherent transmission, which really works best if you do not have dispersion compensation, and it works best if you have the flexibility to squeeze the channels together or move them apart at will, and are not, to whatever values are optimized for the particular system that you're on, and not be constrained to a fixed grid, which was used in previous systems. The previous systems were all deployed using a standardized wavelength grid that initially could support up to 40 wavelengths with 100 gigahertz spacing, about 0.8 of a nanometer between individual channels, was later augmented to support 50 gigahertz spacing up to 80 wavelengths in the typical amplifier band. But the Flex system is not constrained to those specific wavelengths. You can choose the optimum wavelength for the optical channel spacing and the optical width of each, spectral width of each channel, depending on the system that you're deploying. And this, in fact, gives us the flexibility. We know coming down the road, there are systems with even higher bit rates, more complex modulation schemes that use different amounts of optical spectrum. These Flex systems give us the flexibility, if you will, to deploy those systems in the future. So now let's look at the light sources that go on those transmission systems. As I mentioned, in 2000, we were deploying these OC192 DWDM transponders. Again, it's OC192 because that's all that was available in the industry. You couldn't buy, nobody made a 10 gig E DWDM transponder, or certainly not a 10 gig E DWDM pluggable optic that would go into a router. The routers didn't even have 10 gig ports at the time. In 2007, we began to migrate to 10 gig E, and we used, again, a transponder. Don't like transponders, but that's all that was available at the time. Finally, 2 years later, in 2009, the industry developed some pluggable transceivers, that allowed true IP over DWDM. This was a somewhat larger than desired form factor. It was called the XFP, but that was available in 2009. It took another 5 years to 2013 before the industry evolved to be able to support a smaller form factor pluggable, the so-called SFP, which is pretty much the industry standard for high density 10 gig E ports. And so the high density cards that we were deploying used SFPs. So in order to be able to use IP over DWDM with those, we had to wait until 2013 when that was available. In 2015, as I mentioned, we started migrating a lot of the systems to 100 gig, particularly our backbone systems. And unfortunately, that required us to go back to transponders again. There were no 100 gig, and today there are still no 100 gig transceivers that plug directly into a 100 gig port in a router. So we started out with transponder cards that could support 100 gig per wavelength. In 2017, there were some improvements in the technology, and we deployed cards that could support 200 gigs per wavelength, depending on the distance that you were going over some metro, over basically all metro systems. We could multiplex 200 gig router ports into a 200 gig DWDM signal and transport those over metro distances, and sometimes even over intercity distances if the cities were not too far apart, maybe a couple of 100 kilometers at most. In 2019, we began deploying the latest generation of transponder cards, at least from Cisco, and these are the ones that I mentioned before that could go up to actually 600 gigs per second, but over a long haul, over an intercity distance, they're limited typically to about 400 gigs, maybe 500 gigs in some cases. But today we're deploying these cards as the only thing that we're deploying in our long haul backbone. And typically, depending on the distance that we're going, we can get between 200 and 400 gigs per wavelength. And actually, as of today, about 97% of our intercity backbone traffic throughout the world is carried over 100 gig links. It's about 93% of the ports that are on the backbone are 100 gig, but if the higher capacity ports are the ones that are 100 gigs, so it's about 97% of the traffic. Now let's look at the metro transport systems, the evolution there. This is really even almost embarrassing when you think about it today, but if you go back to 2000, you could not even get, there were no gig-E transponders or certainly pluggables that you could deploy over a metro distance. All the DWDM technology throughout the 1990s was developed for these amplified backbone systems, and so those were SONET SDH systems. So in 2000, in order to get gig-E's between our core routers and our edge routers, we actually had to multiplex 2 gig-E's into an OC48 just so that we could put those signals onto a DWDM optical wavelength. These systems were passive systems. We used passive filters. We had some systems that were even capable of operating over a single fiber, not a pair of fibers, using bidirectional transmission. We transmit light at one wavelength in one direction and receive light at a different wavelength in the other direction. A lot of our early metro rings were single fiber using that technology. Finally, in 2002, the industry developed IP over WDM at the gig-E level. These were initially using a technology called CWDM, not DWDM. CWDM stands for coarse wavelength division multiplexing, and it's still using different colors of light, different wavelengths to combine several signals on one fiber. But if you're going over a metro distance in particular, and you're not worried about having to go through optical amplifiers, you can you have a much broader range of wavelengths that you can choose. You can space the wavelengths further apart. They're spaced about every 20 nanometers instead of every 0.8 of a nanometer or 0.4 of a nanometer. And that leads to lower cost components. And so that's what was initially available starting in about 2002. So at that point, we switched from using the OC48 transponders to true IP over DWDM using these gig-E optics that plug directly into the routers and the swouters. In 2007, there were DWDM versions of these optics available in the small pluggable form factor that I talked about before. And in 2009, there were 10 gig DWDM optics available, again, initially in this XFP, the larger form factor, and in 2013 in the SFP 10G form factor. Again, this allowed us to migrate to high density 10 gig ports with transceivers that plug directly into the routers. For our metro rings, initially, as I mentioned, these started out with GigE between the node and or the metro node and the core router. In some cases, we needed to provide more capacity. We could either drop a second wavelength or even a third wavelength, second or third GigE. But in some cases, we would upgrade those to simply upgrade the wavelengths to 10 GigE instead of GigE. So the architecture is very scalable. We started building what we call concatenated 10 gig rings in high density multi-tenant office buildings. So areas like New York, Chicago, in fact, in most of our big cities in the US, where we had lots of office buildings, the customers were buying predominantly FE and GigE ports there. We were able to get better performance and better cost effective, make the network more cost effective by building, by building concatenated rings with a single 10 GigE that connects 4, 6, 8 or so buildings. In 2015, for our higher capacity nodes, particularly large data centers, we started using the NCS2K 100 gig transport, the same equipment that we used in the backbone. And as I mentioned before, that went through a couple of evolutions. And today we can deploy in metro areas with these same transponders that we're using in the long haul. We can get 600 gig per optical wavelength over metro distances. Also, for the metro rings, over the last several years, there's been an increasing demand in multi-tenant office buildings for 10 GigE ports. A lot of our metro customers or business customers are now looking for 10 GigE ports. That's a little bit difficult to provision on these concatenated 10 gig rings. So we're in the middle of a process now using this ASR 9901 router, which has 100 gig ports. We're converting our metro 10 GigE concatenated rings to 100 GigE concatenated rings. We expect to have most of that conversion done over the next 2 years. Now, again, I mentioned earlier that most of our metro systems are deployed over passive systems that don't use optical amplifiers, but about 10%, about 10% of the metro systems use the same MSTP amplifier technology that we use in the long haul. So as our network initially focused on, you do the easiest things first. So we focused on buildings that were close to the hub using smaller rings. But as the network has expanded, we're reaching out and trying to connect buildings that are farther away from our hub sites. And some of those are requiring amplified systems in about 10% of the case. But we use the same technology, the same equipment that we use in the long haul, that we redeploy that in the metro areas. Let me talk about some of the challenges that we face and some of the opportunities, some of the solutions that we're looking at. As I've mentioned several times now, IP over DWDM is the holy grail. That's the lowest cost, best power efficiency that we can achieve. But today, unfortunately, it's not available for 100 GigE ports. There is a technology that the industry is working on today called 400G ZR Plus, ZR and ZR Plus. This actually is a pluggable optic that can go in 100 gig router ports. They have to be specially designed ports that are designed to accommodate the higher power of these what are called SFP double density pluggable optics. But these can support line rates up to 400 gigabits per second on a coherent DWDM optical wavelength. Now, there are some technical challenges. The products that are coming to the market in, say, the second half of this year, are coming to the market fairly soon, have very, very low transmit power values, which means that you pretty much can't use them. Well, you can't use them in a passive system. They have to be used in an amplified system. And the power level, the transmit power levels are about 10 times lower than the typical power levels for a 10 gig system. So that makes it difficult even to use these, to mix these 400 gig signals with 10 gig signals on the same system, even if it's an amplified system. So there are a lot of details that still have to be worked out. The industry is, this is a big issue for the entire industry. So the industry is working on improving this technology. I expect within another 12 to 18 months, there will be pluggables available that have better, higher power levels that make this a little easier to implement. So we're evaluating and watching this technology closely to try to achieve 100 gig IP over DWDM. The other nice thing about these optics is they're 400 gig optics. They can operate up to 400 gig line rate, but much like the transponders that we have, the 600 gig transponders that we have, you can back off the line rate. You can operate these at 400 over certain distances, over 300 gig at longer distances, over 200 gig at even longer distances, and so on. So they're flexible, and we're really looking forward to evaluating and being able to deploy this technology practically probably in another year or so. I mentioned that we are deploying some of the new routers, the ASR 9902 and 9903, beginning in the second half of this year. And this will allow us to increase the availability and the cost effectiveness of 100 gig ports at small to medium data centers. And also the 9901 router that we're already deploying is allowing us to increase the availability and cost effectiveness of 10 gig ports in multi-tenant office buildings. So I've talked about the technology evolution over the past 20 years. Let me kind of look now at the business model evolution. Certainly, our business model has grown in geographical scope. Our initial focus was on 20 US cities, 20 markets in the US, and that's grown today to 207 markets in 48 countries. We've added a few products to our portfolio. Initially, we had layer 3 service only at fixed GigE, FE, GigE, eventually 10 gig wavelengths. We've added a layer 2 service, as I mentioned, but that layer 2 service is deployed using a technology called E over MPLS on the same routers that are designed and optimized for layer 3. So it's an overlay on our layer 3 network. As I mentioned, we've added off-net service to be able to offer full portfolio to customers who are do not have all their locations in our on-net buildings. We've added co-location. We now have 54 Cogent data centers available. We've added burstable, that is usage-based billing as an option. We've added things like link aggregation as an option. That's where you can take several physical ports and bind them together to make them look like one larger virtual port. So some modifications to the product set, but all in all, we've had a big geographical expansion, much higher bit rates, higher port line speeds, like 100 gig E available now, but not really much change in our overall business model. It's not much different than, again, what David sketched out to me on the back of a napkin in 2019. We are still committed to providing the lowest cost per routed bit mile in the industry, and we're continuing to do that. So at this point, I will take any questions that you have. Thank you very much for your attention.
Okay, Dr. Coomer, we do have a couple questions that came in. The first question asks, what would prevent a new Cogent from starting up today? Any obstacles?
Well, I mean, there's the blueprint is out there now. Certainly other companies can and have tried to copy our business model. Basically, we were there first. We've got a pretty large established network now, but basically our secret sauce is pretty simple. It's not that secret. So others could do the same thing.
Okay, thank you very much. Our next question asks, what is the benefit to me as a potential customer for Cogent to have a single network architecture?
It's just the simplicity that the single network architecture, the small focused product set allows us to offer very high quality at the lowest cost. I mean, normally somebody says, I'm going to give you the highest quality at the industry at the lowest cost in the industry. You say, yeah, right. But with this simple product set, that actually allows us to do that.
Okay, very good. Thank you very much, Dr. Coomer. That concludes all the questions that have come in today. So I want to thank you very much for your time and your presentation, and we'll go ahead and conclude the live stream now.
Great.